Good morning and good afternoon, everyone. We welcome you to our Pacific Wash webinar. This is the fourth of a series this 2024, and today we'll be exploring seawater desalination options in the Pacific for emergency and remote applications. Seawater desalination is an increasingly appealing water source for communities and populations located in coastal areas. Clearly, there are advantages of desalination. It is climate dependent, highly adaptable, and can mobilize unlimited resources. Seawater desalination can also reduce the needs for conveyance and raw water storage compared to surface water options. On the downside, the option for desalination is too costly, requiring intensive energy for many cities. But this has been reversed with efficiency improvements, for example, technology advancement on energy recovery system, and the increasing price of other sources have made this option relevant and competitive. My name is Carl Galling, an urban development specialist here at ADB, and I'm pleased to facilitate our session today as we are examples from our Pacific partners on the application of seawater desalination in the context of emergencies and remote operation. Now, before we proceed, may I remind you of some housekeeping rules? If you could flip to the next slide, Sinead. It would be nice to identify yourself in your profile or indicate your organization. We would encourage you to remain on mute while presentations are happening, but please raise your hand if you do have questions. We'll acknowledge you to speak, and we encourage you to ask questions in the middle of presentations through the chat box. You can also post your comments and remarks or even questions. There will be question and answer portion at the end of the presentation, so we'll have a bit of discussion after the presenters have made their presentations. Now, to just give a rundown of the webinar program in the next hour, we will be having opening remarks quickly from ADB and PWWA, after which I'll be introducing the presenters. Again, we'll have Q&A session, and then we'll have a bit of some poll to hear feedback from your end and have a group photo. So without further ado, may I call on our first from ADB, Satoshi Ishii, the Director of Strategy and Partnership from our water and urban development sectors. Previously, Satoshi has served as ADB's urban water sector focal and head of the portfolio management unit in Vietnam. By training, he is an environmental engineer and urban sector expert with more than 18 years of experience, including 15 years of development finance institutions. He has designed and managed city water, sanitation, transport, energy, and infrastructure projects in Southeast Asian countries. His areas of expertise include infrastructure, finance, climate change, mitigation and adaptation, and environmental pollution control and management. Prior to joining ADB in 2009, he worked for the Japan Bank for International Cooperation and Japan International Cooperation Agency and the United Nations and the University of Tokyo. So without further ado, may we call on you, Director Satoshi Ishii.
Thank you. Thank you, Carl. And thank you, Cara, for the very comprehensive introduction of myself. First of all, I'd like to really thank everyone. I'm really happy to have this opportunity opening this very important webinar that Nita has been talking a lot about it. And then I'm finally, coming to, opening this webinar, which is really great. Again, so it's my really great pleasure to welcome you to the fourth Pacific Wash webinar for 2024. Once again, we are proud of co-host this session with our partners, the Pacific Water and Wastewater Association. I'd like to begin by acknowledging our colleagues from utilities and government agencies across the Pacific, along with representatives from development partners and colleagues from the ADB joining us today. Today's session will focus on the topic of critical importance of many Pacific utilities and communities, desalination. As we know, water scarcity remains one of the most pressing challenges in the region, particularly for remote communities that are vulnerable to droughts. Desalination offers a transformative solution by converting seawater into potable water, providing a steady and reliable source of safe drinking water. However, while the potential is significant, there are also important considerations. The energy demands, operational costs, technical capacity needed to install and maintain desalination unit present challenges that must be carefully evaluated. Today's webinar will delve into these complexities, exploring both the emergency application of desalination and the operation and maintenance of system in remote settings. I encourage you all to engage actively in today's discussion as we explore how desalination can play a pivotal role in building water resilience in Pacific communities. Thank you again for joining us, and I'm really looking forward and engaging an insightful session. Thank you.
Thanks so much, Director Satoshi. From the Pacific Water and Wastewater Association side, may I call on, needs no further introduction, the CEO for PWWA, Lucia Cefo-Leo.
Thank you, Carl. Well, good morning, good afternoon to those of you on this side of the world. Talofa, and welcome everyone to this fourth webinar series for this year. I am happy to see a lot of you here on this platform, as the last time we met was at the conference in the Cook Islands a month ago. And I'd like to particularly give a warm welcome to the ADB staff and also to our member utilities whom I can see are present here today. But firstly, let me say I am also very proud and grateful for this collaboration with ADB. We are fortunate to have collaborated in bringing industry experts and utilities together over a little over a period of maybe 3 years now. The sharing of knowledge and experiences has been very valuable and impactful for utilities in the Pacific through this platform. Today, we discuss a topic that is rather interesting and fascinating that I know very little about, converting seawater into potable water or desalination. We recently had the BWWA annual conference that focused on resilient water in light of climate change and its impact on our Pacifica region. Finding solutions and the technologies that are affordable and adaptable to our region is not easy. And this technology or option, which is the topic for today, is touted to support water resilience and sustainability in the Pacific. I am keen to hear from the experts and to listen to your feedback and comments. So without further ado, I will hand it over now to our experienced facilitator, Eka, to introduce our speakers for today. And thank you for your attention, everyone.
Thank you so much. Lucia, I think that puts us in a good proper context as we discuss the topic of seawater desalination today. Now, I'll just quickly introduce our speakers, starting with Dr. Matt Francis, who is the Director of Water Chemistry Design and Capacity Development Lead at Moerk Water Solutions. Dr. Matt Francis is the Head of Design at Moerk Water Solutions, Asia Pacific. He has a PhD in chemistry and has worked for more than 20 years designing water treatment solutions for surface water, groundwater, and seawater sources. Moerk Water Solutions Asia Pacific is an Australian-based water treatment company that designs and builds sustainable water treatment systems for remote communities, the healthcare sector, and industrial clients. Moerk Water focuses on local operator training, and we'll hear more from Matt on how they do that with their clients, and have service partner across Pacific region to ensure the long-term operation of their units. So without further ado, I'll hand over to you, Matt.
Thanks very much for that, Carl. Just bringing my slides up. There we go. All right, so I have been asked to give a brief background into desalination because I understand there are some people on this webinar who aren't desalination experts. I won't spend too long on this. Basically, the need for it, what technologies we use, and then I'll go straight into how we apply this to emergency contexts. So, there we go. What we're seeing across the world, really, not just in the Pacific, but in all the dry places we work, is that we are seeing an increasing need for desalination. So Western Australia, where I'm based, we've just brought online our third municipal seawater desalination plant. I think more than 60% of our water supply is going to come from seawater desalination. And that's because it doesn't rain in Western Australia anymore. We haven't had rain go into our dams since 1970. So we've had to move to seawater desal because the rain doesn't fall anymore. And this is something we're seeing a lot, particularly in remote Pacific islands. They've relied historically on rainfall and it's becoming less reliable. We're also seeing increasing salinity of groundwater. This is a problem we see a lot in Africa, where groundwater sources which were traditionally fresh are now becoming increasingly salty. And once water is salty, you're generally going to need some form of desalination. We are also seeing more call for emergency desal systems in the wake of natural disasters. Often distribution networks can be damaged or water treatment systems themselves can be damaged. And as a stopgap solution, we'll see an emergency seawater desal rolled out. So although, as Carl said, although there are issues around desalination, it is an abundant source that can provide potable water. So generally, we look at two different types of installations: permanent installations. So what we've got in Western Australia, the water problem's not going to be solved, so you just need to install more capacity. There's no surface or groundwater available, so you're going to treat seawater. And then the portable units, which is more for short-term situations. So you have a slightly longer dry season than normal, so you might deploy a seawater desalination system to get you through the dry season when the rain's falling again. So when we look at how we desalinate water, there's a whole range of different technologies. They're based on thermal technologies, based on electrical technologies, and membrane filtration technologies. Of these, it pretty much depends how much you're paying for energy, and that will generally determine which technique you're going to use. So in the Middle East, we see that energy is quite cheap, and so they more use thermal technologies like multi-stage flash or multiple effect distillation. But for the rest of the world, when you are worried about the cost of energy, you're predominantly going to use membrane filtration and specifically reverse osmosis. When we look specifically at emergency or even remote contexts, we generally see there are two main options. So you've got a solar still, where essentially you put seawater into this plastic dome. The heat of the sun evaporates drinking water off the seawater, which condenses on the outside of the dome, and you can collect that to drink. And then reverse osmosis, which I will get into in more detail. So reverse osmosis works. It's actually quite a simple process where the forward osmosis process, you have clean water going across the membrane into salty water. That's forward osmosis, where you have low salinity water moving across the membrane to high salinity water. This movement induces a pressure, a head of pressure as the water column rises. This is the osmotic pressure. If you reverse this process by overcoming that osmotic pressure, pushing down on the side of the salty water, you'll actually force clean water back through the membrane. And that's all reverse osmosis is where providing a higher hydraulic pressure through electrical pumps to force water back across the membrane. So if you look at the table I've got on this slide, you can see the osmotic pressure for different types of salty waters. So you've got contaminated freshwater, brackish water, which is anything from freshwater to seawater, and then seawater. And as you can see, as we add more salt, that pressure we need to overcome gets higher and higher. And so the hydraulic pressure we need to apply with our pumps gets higher and higher and higher. And that's where the energy cost from desalination comes from. So when we're picking between solar stills or reverse osmosis, we generally see solar stills as very much a personal use device in emergency situations. These are a great thing to have on a boat in case your water maker breaks down. It is pretty much limited to about 2 litres a day, so it is just survival. It's just drinking water for survival. You can make bigger systems, but you are always going to be limited to about 6 litres per metre squared of evaporation area. So we generally say these are good units for individuals, maybe for a house, not much bigger. Reverse osmosis, you can get reverse osmosis systems that will produce 5 litres a day, but generally when you're talking economical benefits, they're going to start at about 30 litres a day. So they're much better for a few households, up to communities, up to municipal scale. So generally when we're picking an option, it's going to start with how many people do we need to serve. Next 2 slides, I'm just going to quickly talk about the deployment of reverse osmosis, and this is regardless of context. This is municipal plants, this is small remote plants, this is emergency plants. The process itself, as I said, is fairly simple. We feed pressurized seawater across these membranes, and you produce 2 streams. You produce your potable water and you produce a waste stream. So the things you need to consider is, where are you getting your pressurized seawater from? Does it need pre-treatment? Where are you sucking it from? How are you getting that pressure involved? Then you've got to think of the 2 product streams. How are you storing your product? Are you going to then distribute it? Are you going to disinfect it? And for your waste stream, how are you going to get rid of this stream? Do you need to consider the salinity of the stream or the volume of the stream? So that's the process itself. You also need to think of the supporting infrastructure around the reverse osmosis system. So reverse osmosis systems, as we said, use a lot of energy. They are the most energy intensive of the water treatment methods that are quite commonly used. So generally for seawater reverse osmosis, you need between 3 and 5 kilowatt hours for every 1,000 litres of per minute you produce, which is a lot of energy when you consider traditional water treatment methods. And the smaller scale these systems get, as you start moving towards those emergency systems, you generally need more and more energy, because small high pressure pumps are not as efficient as big high pressure pumps. You've got to use more energy. So that's just the power. You also need to consider your maintenance requirements. So how are you going to maintain the system? And again, this is regardless of whether you're talking municipal, remote or emergency. And how are you going to train your maintenance staff and your operational staff to operate these units? And lastly, you need to consider, how are you getting this unit to site? How are you installing it? And how are you going to house the unit? It's all fairly simple stuff. When we look at the emergency context specifically, this does change slightly. So for the feed water system, generally we're going to be talking an ocean intake. We're talking seawater reverse osmosis. And you're going to have to be thinking, if it's in the wake of a natural disaster, you might have increased sediment load, you might have increased bacterial load, you might also have fuel spills or something that you need to consider on your pre-treatment system. Membranes are very sensitive, and you need to carefully consider what you're going to be putting across the membrane. For the water you're going to produce, how are you going to distribute the water? If it's an emergency situation, are people just going to be coming up with their containers to fill? Are you going to be putting it in temporary bladders, or are there storage tanks on site you can use? And then again, the reject, you need to consider, how are you going to be getting rid of this concentrate we're producing? So ocean discharge is generally the best for seawater reverse osmosis, but there are salinity limits. So this all determines how much water you can pull out of the seawater you're treating, because if you pull too much water out, you're going to have a very, very salty waste stream you need to deal with, and that can cause real issues when you try and mix it back into the ocean. In terms of power, for small portable emergency desalination systems, you can use renewables. So for example, we have a 30 litre an hour emergency unit that requires 4 foldable solar panels. They're quite small portable panels. As you get up in scale though, because of the power demand, you can't really use renewables to power these systems. So if your local grid's down, you're going to probably have to bring a generator on site with you to give you the power you need to run these systems. So then you've got all the things around you're having to bring fuel with you, whether it's petrol or diesel, and supporting the infrastructure of that generator as well as the infrastructure of that water treatment system. If you're running these systems high recovery, you're probably going to need some chemicals on site as well. So you're going to have to make sure that your dosing system's working fine and that you also have a source of that chemical. And then transportation. So the more and more we add to these systems, so that we've got a power system, we've got chemicals, we've got the water treatment system itself, all of that needs to be transported to site. Because if any one of those factors isn't transported to site, the system's not going to work. And then around all of this is your operation and maintenance training. So you're having to make sure that your operator knows what to do, how to make sure he or she is using the feed system correctly, producing the product water, producing the reject stream, and dealing with that correctly. And then we get to the big difference for emergency systems, which is storage. So emergency systems differ from remote or municipal systems in that they're not used all the time. Reverse osmosis systems love to be used day in, day out, and are really good for providing a base load supply of water. If you do need to pack down a reverse osmosis system, the best thing you can do is to drain the entire system, pull the membrane out, and store it in a specialty chemical called sodium metabisulfite. And essentially you soak it in a 1% solution for an hour, drain it, and then seal it away from air. That should preserve that membrane for 3 months. If you need it stored for longer, generally you're going to have to keep an eye on the pH of that storage solution, and potentially you might need to give it another rinse, give it another preservation to make sure your membrane's ready for when you need to deploy the unit. You're also going to need to store the unit and make sure you don't lose any of the bits. We've had that happen in the past where people have actually lost the membrane for the reverse osmosis unit, which wasn't great when they got to site and wanted to use it. And if you're having to use portable power generators, if you're unable to use portable renewable energy, you're going to have to service those generators to make sure they're going to work when you deploy them in field. I did want to also touch on training, because training is such an important part for emergency deployment. What we find is that the training required to support an emergency unit is actually more than what we see for training for a remote unit. So training for remote units, generally it's just day in, day out operation. This system works all the time. If you're talking about an emergency unit, you're not just talking about operation, you're also talking about maintenance, you're also talking about storage, and you're also talking about all the inventory plans around that. So what we've also found is that you need comprehensive asset maintenance plans in place, and that you need refresher training. If you're only using this system once a year to get you through a dry season, you need to make sure you're ready to deploy, and you can't be like, as the emergency hits, oh, how do I use that reverse osmosis system sitting on the shelf? This all needs to be done in addition to educating the community as to where this water is coming from, to make sure there's no issues around the actual deployment of the asset. For my last slide, I did just want to touch on how remote installations differ from emergency deployment, just to show kind of how a system running all the time, even if it's in a remote place, will differ from this emergency deployment we've been talking about. So if you have a remote installation, generally it's going to be better to produce your energy locally, whether that's renewables or an on-site generator that at least doesn't have to be deployed. And as I alluded to before, training is actually better separated into an operation module and then a maintenance module or a servicing module. So daily operations happen on site and don't need to be done to the same kind of degree that a service or maintenance training will have to be done. Transport and long-term storage, obviously not required because the system is on site for remote installation, and you're going to have permanent feed and storage tanks on site to deliver all of the infrastructure around the system. So that's all I really wanted to touch on. Happy to answer any questions around this, and I'll hand over to our next speaker.
Thank you so much, Matt, for making that brief but very rich. I've taken down some notes because this is a very interesting points that you've raised, especially for us who are not quite familiar with reverse osmosis and operations of membrane filtration. But I think you've mentioned a lot of things there. It's important that you've made an initial differentiation between permanent versus portable installation, especially for emergency cases. Before we proceed, I wanted to just acknowledge those who've connected and participated with us today. People across the Pacific from Fiji, Solomon Islands, our utility partners from FSM, water from PNG and Tonga, but also our regional partners, SPC, Water, Korea Water Resources Corporation. Interesting. So thanks so much. We encourage you to please post your questions from that initial presentation of Matt. And for now, I'll be introducing our next speaker. Moerk Hiram is the General Manager for Water Operations of Nauru Utilities Corporation. Moerk Hiram began his work with NUC since 2008 as a technician. For more than 10 years as a technician, he has devoted most of his time as part of a team involved in operating and maintaining the reverse osmosis plants with all its auxiliary. During his time with Nauru Utilities Corporation, Moerk worked his way up and became the team leader, whereby his primary role was taking lead in problem-solving situations and ensuring effective and efficient operations of the desalination plant operations. Since 2021, Moerk has been the GM for water operations, where his primary role is more into strategic planning, project management, team performance, and development. So without further ado, we would love to hear more from you, Moerk. Please, you have the floor.
Thank you, Ed Carl. I'll just proceed with the presentations. Yes, okay. My first slide is just a brief overview of Nauru, just for you to understand what are we dealing with in terms of water supply. So Nauru is a very small island, 21 square kilometers, with a population of around 13,000 people. Its location, it's in the central of the Pacific. A bit of background in terms of water resources in Nauru. As you know, Nauru is a remote island country situated in the middle of the Great Pacific Ocean with a land size not larger than an average city in a developed country around the world. So since Nauru's independence, 1968, water security for the people has always been a challenge, given the geography and the context of the island, whereby at times Nauru had to import fresh water from neighboring countries in the region, until when desalination was introduced to Nauru in the mid-90s. So, therefore, up till today, the island continues to grow in reliance on desalinated water, besides other water sources such as the rainwater, imported water, bottled water, brackish water, and seawater. So this is a bit of history, evolution of our desalination processes. So during 1993, we have the first desalination that was installed. It's a thermal desal plant, and it went on for many years, and then until we had the first reverse osmosis, containerized reverse osmosis, as part of like a emergency response at the time when Nauru experienced economic collapse. So we had to import those containerized RO units. So over the span of 20-year plus desalination evolution, there's been a lot of adaptation and technical support for our people to understand the processes and the systems. And Throughout the years, by 2021, we've received the new RO plant, which is the biggest one. It can produce 1,800 cubes per day. So this is a bit of history of Nauru in terms of desalination. This slide, just a bit of something around means and strategies in terms of to support our visions, our goals. So firstly, we've identified our target groups. So we had to improve our strategic business unit, which is the water operations here at Nauru Utilities. Target groups were the production, storage, and delivery improvement. So the objective was to improve effectiveness, efficiency of the water business, and operation and maintenance, productivity, and of course customer satisfaction. So in order for us to get this forward, we needed to identify our strengths, and we need to take a snapshot of ourselves and what we need to do, and to resource ourselves and take on those objectives. And as you can see on the slide, on the right-hand side of the column, we have the expected outcomes. We needed to achieve those things. Some of those points there were being achieved, and some are still underway. And we continue to undertake all the effort that what's needed to be done with the means and strength that we have in order for us to improve and meet the targets. This slide is just representation of illustrate RO system pre-treatment process. So firstly, if you want to have an RO, you have to have a good pre-treatment process, because as you know, the RO membranes are very fine filter, and so you have to have a good pre-treatment process. So in the diagram, as you see, we have the raw water, and then the strainer, and then into the feed water tank, the feed pump, and then the multimeter filter. That's the first step of filtration. Takes away the particles, the bigger particles, and then we have the cartridge filters. It steps down it's more filtration there on the cartridge filter. And after that, we have the pre-treated water. So that's the water that's going to the RO for the RO to take place. So yes, but most of the ROs nowadays, this pre-treatment process is built into the RO. If you have a containerized RO, it's a built-in, it's in there. And I think in larger plants, this is sort of separated. It comes in different train or different skip rather than built in a container. So yeah, this is a basic process of pre-treatment. As we have learned from the previous slide, we as you can see on this one, we have the pre-treated water that's coming in through to the high pressure pump and into the membrane, semi-permeable membrane. Inside the membrane, as Matt was explaining it earlier in the presentations, we have the permeate outlet as well as the concentrate, which is the brine, and this is throttled around by the concentrated valve. So this controls the osmotic process to ensure that there is this correct flow with the correct pressures and achieve the most efficient and correct outputs from concentrate and permeate. And down below you have the recovery. It's just a basic recovery formula. For our case, one of our RO units, we have a flow of 33 cubes per hour, and we have the feed flow of 90 cubes per hour. The feed flow is coming in as the pre-treated water into the RO. So if you apply the formula on that, you have a 36% recovery. So that basically means the raw water that's come in, 36% of that has been extracted as potable water, and the remaining 64% is concentrate. It's the brine that's going out to as drain to waste, if you like. So yeah, that's the basic process of the RO. And further to that, just for those who are new to this technology, I can assure you that the RO system is basically comprised or made up of pumps, filters, and membranes, and it's designed in a way friendly to operators. Just plug and play if you like. And however, as a technician, for me, technician standpoint, it's important to understand how the system works, the different components, because when things starts to fail, you know what to do, and even you know how to troubleshoot when there's fault. Yeah, it's important to understand the RO process itself. Okay, this is a bit of a maintenance plan we have here, and it's an annual preventative maintenance schedule. So this is a full year calendar. In yellow, those are the days in the year, and as you can see in the months, progressive months, we have the blue color, the yellow, the orange, green, and all that. Those are the schedule for services for servicing the ROs that we have here. So on your right-hand corner of this slide, you have the sort of legends for those color codes, like for tasks and frequency of those services that you do in order to achieve an effective RO operation. You have to have a good maintenance plan, and yeah, so you have to have a good team as well, and have a good reporting and data collection as well. This is a bit of a KPI that we monitor every month. We have on your left-hand column, left-hand side of the sheet, we have the KPIs there: water production and water delivery, as well as the electricity usage of the plant, of the RO plant. So we know how much water has been produced from each of the ROs that we have. Every month, as the year progresses, and the availability as well, we capture that just to make sure that we are maintaining the ROs, make sure they're always available. So there's sheets that supports this report. So it's good to have something in place, a reporting data collection KPI, as you like, for the operations to to tell you what's happening in your operation. And at the bottom, we have the electricity usage. So its average total electricity usage is around 120,000 kilowatt hours. As you can see down below, so that's been captured as well. There's a lot of energy has been used on the ROs. So it's important to capture that as well, just to know what's happening and what are you dealing with. This is the team that we have here, the structure there and the team. So that's myself there on top, GM water operation, and we have the services manager. And then we have two sections. We have the team leader for water distribution and the team leader for water production. So under the team leader water production, we have the team there that shows there on the slide. We have the team leader, the RO technician, assistant RO technician, trainee RO technician, RO operator, trainee RO operator, and the tradesman mechanic. So these people look after this the operation and maintenance of the RO plant. In terms of capacity building, it's really important to have a good team, and it's really important to identify individuals who have that background with multi-skill, they tradespeople with background, electrical, mechanical, plumbing, and all that. Anything that associates with the operation and maintenance of the RO, it's really good to have those kind of individuals. And yes, so as I've said earlier, one of the most important factors in having a good and committed team is identifying and empowering the right individuals, internally or externally, who are keen, willing to learn and contribute to serving the people, to which is one of our core values here at NUC. So below are some of the recommended training package for our technicians, which NUC technicians have acquired. One is the Certificate 4 in Plant Maintenance Engineering. That's in Fiji National University. That one I've undertaken that back in the years. It's a really good course. It involves a lot of plant and maintenance work across all the engineering, mechanical engineering. We have we've done machining, refrigeration and maintenance, and mechanical, electrical as well, PLC. So all of those things that are very important for in an RO. And also we have the Certificate 3 in water industry that is done online, Siemens and Bristol. My RO technician has done this, and it's very good. And also the AMS training solutions for RO specialist training. So, yep. Okay, I think I'm towards my end of my slides now. Just a bit of photos here. On the left hand, we have the storage tanks. Those are our storage tanks. These are 270,000 liters each. And in the middle photo, we have the seawater intake pumps. Those are the pumps that bring in the raw water. And then we have the RO plant, 1,800 cubes a day RO plant. That's the photo of the MMF. That's the multimedia filter. I think that's it. Thank you very much. I'll hand this over to Ed Carl.
Thank you so much, Mark. That was very useful. I think you're beginning to convince us how reverse osmosis seawater reverse osmosis should be seen as a simple system and not that complicated. As you put it, it's a collection of pumps, pipes, filter membranes. something that could be easily operated. And I think that's what Matt is also telling us in terms of the emergency installation. I'll be interested to gather a few of the questions provided in the chat box. I think there's one from Vili. Matt, you've initially responded to that, but the question I think is, if your source water is brackish, does the brine or rejected flow, can that be used for other purposes such as agricultural use? Matt, I think you initially responded, but Mark, there might be some experience also of reuse for your brine.
Well, at the moment for us, it's just going out straight to back to the ocean, and there's a study going on from government officials here in Nauru to see possibilities for utilizing that brine to make salt out of it.
I'll get into that later and maybe ask more about the impacts of the outputs of desalination. But Mark, there's a question for you here for your system. What are you pre-treating? Is it for primary filtering of particulates? You're muted, Matt. I think that's also for Mark.
Sorry, can you say that again?
There's a question in the chat. You've mentioned about pre-treatment in your system, right? Is that pre-treatment primarily filtering for particulates?
Yes. Is it reference to the pre-filtration? Yes.
Right.
If it does, it takes away like just about anything that potentially can come into the screens at the intake pumps from the sea. Sometimes we experience like seaweeds or even fish sometimes sips through, and they get blocked out in the screens. So that's one of the maintenance that we do. We check our basket filters. The first screening of the seawater, we check the basket filters every month to make sure that there's no seaweeds or anything that's in the larger particles are not there.
I think Matt mentioned an important point earlier in terms of the quality of seawater that flows into the system. So the more the saltier that water is, the more energy is required, right, to desalinate that water. So if you do have sources of water that are slightly brackish, then that would be more advantageous rather than directly getting water from the sea. Is that correct?
Yeah, that's actually a really good question, Carl. So what we often recommend is that seawater desalination is the last port of call. Treat your surface water, treat your brackish groundwater, and then treat seawater. But what we often find is that groundwater doesn't have sufficient capacity to support whatever the solution is. So seawater, obviously there's a lot of water in the ocean. And also particularly for emergency contexts, groundwater is obviously harder to access in an emergency context, whereas again, the ocean is just there. So the lowest salinity means lower energy, but it does depend on the location. You know, are there other sources available?
Okay. Sinead, I might just ask you to kindly filter other questions that I might have missed in the chat box, but just wanted to pose this question because we've been talking about the advantages of desalination. It's could be robust and a plug and play system, but let's talk about the main criticisms, mainly on environmental impacts like public acceptability. You have issues on impacts on marine life, right? Impact on coastal areas and marine bays. And I think it's good that you've shown that calculation in terms of that rate of permeate being generated, Mark, which essentially is telling us that the amount of seawater that you're extracting is twice as much of what you actually produce as permeate. And there's also concentrated brine that's produced. So I wonder how you dealt with these issues in your specific projects or implementation, particularly in Nauru. Maybe you can start, Mark, and then I'll ask Matt in emergency situations.
Thanks, Carl. Yes, that is an issue, and I think the most effective way to address this issue is to have the outlet brine spread across rather than putting into one spot. But for our case here in the Pacific, like for Nauru, if you have a desalination plant of a size 1,000 cubes a day, that's compared to other big countries like Singapore, and that's just a fraction when you look at the ratio against the Pacific Ocean itself. So I think what they did in Singapore was that because it's so massive RO plants there, so their outlets were being spread across rather than concentrating into one area in the ocean. So yeah, it's something we're going to look into as well for us to work with the environment people here in Nauru, and yes, that's what we experience here.
No, thanks, Mark. And I'm sure you're not even close to industrial level operations, like you mentioned about Singapore, where they might have larger systems being operated compared to Nauru. But thanks for sharing that experience. Matt, anything from your end in terms of mitigating environmental impacts?
Yeah, so Peter in the chat has actually answered this. So for really high recovery systems, when you are worried about the saline water remixing into the ocean, there are diffusion systems you can use, and obviously you don't want to be disposing of that into a stagnant body of water, because obviously that's not going to mix back in. For emergency context and for remote context, we'll often run our systems low recovery. If you run them low recovery, you don't need to add chemical, because obviously any chemical that goes into an RO is going to come out in the reject stream. It's not going to go across into the permeate. So if you run them low recovery, the salty water that comes out the far side is much lower in salt, and so it remixes quite easily. But obviously there's a balance here, because low recovery systems can cost more energy and are often larger systems. So you've definitely got to work with your customers to figure out what the balance is going to be and how they're going to deal with their reject. But yeah, for emergency systems, I always say run low recovery, because then you can have one line running into the system and then your reject stream straight back into the ocean.
Okay, thanks. Suddenly we do have like several questions posted in the chat box. I'm afraid we cannot pick up everything, but there's a question from Tehon Park. Common maintenance issues encountered for remote desalination. How can you mitigate these challenges? There's one question from Sylvia from Water PNG, which is also an area of interest for me. If you could both provide an answer on this average monthly energy cost to operate your desalination plant. Maybe just a quick answer. Matt? Just put it in the context
well,
of probably
for
production, in the context of the actual water produced on that costing.
we have a budget. We have a maintenance budget that reflects the maintenance and operations of the RO, and it's not. It's costly, as we all know. It's costly to operate an RO plant when you, like for Nauru, when you're entirely reliant on desalination, and you have you have to have a good maintenance plan. And when in terms of costs, I cannot really. I might be wrong if I uh, throw a number here, but I'll look into that and hopefully share it in the near future.
All right. I'm afraid we've run out of time. We have 2 minutes to do our closing. I'm cognizant of the good comments provided, including from Mark Mosselin. We will take note of all these. I think we will stay in touch with this discussion. We do have our contact numbers, and we could facilitate from ADB side these conversations to continue, and any other trainings or discussions we could pursue in the future. But maybe for now, given the time constraint, we'll just proceed with a quick poll. If you could bring that up, Sinead. If you could kindly answer these 2 questions, which would improve the conduct of our webinars in the future. But we would love to hear your feedback, but also write us through email of any comments or feedback that you want us to have improved on, or any topics that you may want to have in the future for webinars related to this technical topic. Okay, how are we doing with the submissions, Sinead?
Good. I'm just going to give everyone another minute. So just a few people have said about sharing the presentations. We have recorded today's webinar, and we'll share the webinar and presentations online. I've just shared the link in the chat, but it will be emailed out too. So you should receive that in email, and the link there is for this webinar, but you will also find the recordings and presentations and summary resources for all our previous webinars there too.
Okay.
Okay.
Thanks, Sinead. Before we take our group photo, may I again thank our 2 resource persons, Dr. Matt Francis from Moerk Water Solutions, and Mark Hiram, the GM for Water Operations at Nauru Utilities Corporation. So thank you so much. Thank you so much for those who attended as well and participated actively. We will be in touch with you. Kindly share the recording of this session for reference of those who weren't able to join us today, but we'll make the link available to everyone.